Okay, welcome back to Calculus 2. So we're going to be looking at some improper integrals right now. So the integral that we are currently looking at is we have the integral from e to infinity of 1 over x times the natural log of x cubed dx. Now, I know that you're going to do this once you get out of Calculus 2 class, but this is the class where they have to like make sure that you're doing it properly and all your notation is correct. And I know you're going to be relaxed about this later on, but for the purposes of this exam, one of the things I'm going to be grading you on is how good is your notation. And I'm sorry for that, but that's like one of those things that we have to do. So when the difference between say less and few. If you say something is lesser than or less than, then it's a quantity that can't be counted. Like you have less time, but if you put it up in the minutes, because minutes can be counted, you have fewer minutes or less time. Okay, you have less mass of sand, you have fewer grams of sand. Okay, so we can have your population. You could have less. Your population could be less, and your population could be smaller. You would have fewer people. Okay, so if you can count them, it's fewer. And this is the class where it makes a big deal about that distinction. Okay, so nowhere else, none of the English-speaking world is ever going to correct you on whether or not you use lesser or fewer. Okay, but there is a difference, and this is the class where we're making that difference. Okay, that you have to be very specific about your notation. So the first thing I'm going to do, pick whatever letter you like to have. I'm going to say we're going to make the limit as b approaches infinity of the integral from e to b of 1 over x ln of x cubed dx. All right. So that's the first thing you're going to do. You see an infinity in here. You're going to replace it with a limit, and you're just going to be able to write the limit. You do not put infinities into an integral. That's not the proper way to do that. Just what the rules are. I know that when you take physics, they're going to do it all the time. When you take engineering classes, they're going to do it all the time. It's not proper, but this is the only class that's ever going to chastise you for not being proper. Okay. But we will chastise you for not being proper. So please don't make me take points away from you for doing this. Tell me it's a limit and work through that way. Okay. So as I'm looking at this, I'm like, oh, this is going to demand some kind of a u substitution. So why don't we set u equal to, so we're going to say let u equals, how about the natural log of x? Okay, that means that du is equal to 1 over x dx. All right, now I'm going to do a couple more things. When x is equal to e, then u is equal to the natural log of e, which is equal to 1, right? Natural log of e, it's 1. When we have x equals b, which is a limit, right? The limit as b goes off to infinity. That's what we're dealing with as, or x goes off to infinity. The limit as x goes off to infinity is going to be equal to b. Okay, let's say x here. Okay, so we're going to be able to do that. So we're going to say when x equals b, okay, when x goes off to infinity, not b, okay, then we're going to have u is equal to the natural log of b, which, if you remember what the graph of natural log looks like, something like this, then as x gets bigger and bigger and bigger, then this also tends towards infinity. Okay, so this could be also replaced with b. Okay, so as x goes off to infinity, u also goes off to infinity. We're going to say b is equal to the limit as u goes off to infinity, and that'll be the same thing. Okay, so b will be the limit as u goes off to infinity, and there'll be the same idea here. So here we go. We have the integral from 1, because remember when x was e, the u was equal to 1, to b, and these are now u limits, limit as b goes off to infinity, okay? Or as u goes off to infinity is b. Let's go ahead and change that a little bit. Um, okay, so b is equal to mu goes off to infinity or tends towards to infinity. Okay, and now we have 1 over natural log. I'm going to go ahead and replace that natural log because that natural log is really u. So I'm going to say this is 1 over u to the 3. And then we have a 1 over x dx here. This whole piece is my du. Okay, so here we have the limit as u goes off to infinity, 1 to b equals b. And then we have u raised to the -3 power. I've put it as this type of an exponent because I want to integrate, and this is the nicer way to integrate. This 1 over x dx, that's du. That's my substitution. Okay, so remember, right? We have du is equal to 1 over x dx. I just substituted it right in there. Now we're ready to integrate. So this is going to be b equals the limit as u goes off to infinity. And now we have u to the -2 over -1 over 2. And we're going from 1 to b. Now it's time to start plugging some things in. First thing I want to do is I'm going to swap my limits of integration to eat this negative sign. So it's really 1/2 u to the -2 from b to 1. Okay, that's you can eat the negative sign and swap your limits of integration. And this is b is equal to the limit as u goes off to infinity. Okay, and then we're going to plug this stuff in. So we have this is equal to 1/2 times, here we have 1 over 1 squared, that's u to the -2, minus 1 over b, technically squared here, right? We just plugged in the b. So this is 1 over, this is getting bigger and bigger and bigger and bigger, right? And this is one of the limits that we know from calculus 1. The limit as x goes off to infinity of 1 over x, that's a limit we know, it's 0. So how this is going to work out is we're going to say, okay, that's equal to b. So again, b is equal to the limit as u goes off to infinity. So we have this, and then we can say this is 1/2 times 1 minus 0. I'll put it in quotation marks for now just to let people know I took the limit. And we're going to get rid of those quotation marks because that's not really nice notation either. But this is just going to be equal to 1 over 2. And then we're all set and done. Okay. So when you have improper integrals, okay, the first thing you're going to do is you're not going to write infinity in the integrand or on the integral sign. You're going to replace that with a letter. That's a thing I'm going to look for. And then you're going to carry that limit down the entire problem. And that is just the way this thing goes. Okay. You have type 1 and type 2 integrals. Type 1, you have infinity or negative infinity up to a constant of some kind of f of x dx. Okay, we have type 2, which is some constant up to infinity, f of x dx. And there's a type 3 that they don't do a whole lot in your book. And that's something like they have 1 over x minus 2. And then we're going to go from like 1 to 3. And then they think they're being clever because as you integrate over 2, there's an infinity there, and you got to watch out for that. You have to like break it up and just say this is 1 to 2 and 2 to 3, and not really 2. It's 2 negative as we go through this, and it's 2 positive a little bit. So we're not quite getting the 2. And you have to go ahead and change limits for this stuff and then make this all happen. So that's type 3. I don't think your book asks you too many type 3 integrals. I'm just going to warn you that they're out there. Okay. I remember I did really well with calculus 2. I took calculus 3 and I got a B because I did not catch this mistake. So it was a project at the end. It was with a lot of points. I was kind of hanging on to that A by the skin of my teeth and by my fingernails. And that was the mistake I made. And it cost, in the end, it eventually cost me a whole letter grade. So don't you, I hope you don't have to learn the lesson that harshly. Okay. So just be careful that in your class, in your textbook, they pretty much deal with type 1 and type 2, which you're going to see the infinity at the end here. And then the sneaky type 3s, which are in there, and the singularity, you're integrating over infinity, is somewhere in the middle of it. So just be really careful about those. But for this integral, it converges. The answer is 1/2. Nice and easy. By the way, let me just add this. In math, converging and diverging. Diverging just means it doesn't settle on a value. It doesn't always mean it goes off to infinity. It just means it doesn't come down to a value we can actually say. Converging, it comes down to a value, okay? But diverging doesn't always mean it goes off to infinity. It just means it doesn't settle for anything. It doesn't like come down. It doesn't decide to keep an actual thing here. So like an integral that would diverge sine x from like, we'll go from negative infinity to positive infinity or something like that. You know, we're going to be looking at the areas for this stuff, and depending on where you picked your point here, you're going to get a positive or a negative area. It never settles, so that's why we have it diverges. It doesn't go off to infinity, because for every positive area you have a negative area, and they will cancel each other out, so it'll stick around zero. But it's not zero. It diverges. It never settles. Okay. So be careful with that. Be careful with type threes. I don't think your book has any, but just be careful. Be on the lookout for them. Okay. Thank you very much for watching the video. We'll see you in the next one, and take care.